All right, so 2.6 molecular and ionic compounds. So these two different words, molecular and ionic, are very specific. Molecular typically means a molecule, but most importantly, we're talking about something that is neutral. And we're going to get to this a little bit, but anything that's molecular contains all nonmetals. Okay, there's not going to be any metals at all in something that is molecular, within reason. So nonmetals and neutral, that's what makes up a molecular compound. They're held together by covalent bonds. We'll get back more into the differences between ionic and molecular. Ionic is going to be ions, which are both charged. So we're going to have both a positive and negative charge species, and we're going to have metals and nonmetals combining together to give us a compound. So molecular is a molecule, an ion, or something that's ionic, we would call a compound. They're slightly different, but they are different. So if we look at an atom, very simply look at an atom, there are two states at which it can be in. An atom, if it has an equal number of protons, there we go, equal number of protons and electrons, 11 each, they're going to cancel each other out. So if I subtract the protons from the electrons, I end up with a 0 charge. All right, the positive of the nucleus and the negative of the shell, of the outer shell, or of the shell outside of the nucleus equalizes out and we have 0 charge. Ion, on the other hand, is when I have an imbalance in the number of electrons or protons. And I'm sure you guys know all this. So in this case, we have 11 positive charges and 10 negative charges. So I have one extra positive charge, making the charge of this +1 in nature. So that has a +1 charge. So ions are charged particles. So an ionic bond, and we probably should talk about it just a little bit. Again, we're going to talk about ionic bonding. But an ionic bond is where you see a transfer of electrons, a complete transfer of electrons. The best example you can always use is sodium and chlorine. Okay, separately, they're very reactive compounds. Sodium is going to essentially give one of its electrons to chlorine. And what you end up with is sodium becomes +1, chlorine becomes -1, and together they form a compound, sodium chloride, which is very stable. So transfer of electrons is what we're looking at with ions. But ultimately, where do those electrons come from? They always come from a different source. We're not really too worried about that. We're going to talk about bonding and that type of thing a little bit later. But for right now, we just want to look at the examples that we have. So cation versus an anion, there's two different types of ions. A cation is a positively charged ion. And an anion is going to be a negatively charged ion. Easy enough. The way to differentiate these two, it worked for me when I was learning this stuff. Simply, there's my positive charge. That little plus right there, and the term cation is always what I used to use to recognize that there was, in fact, this one was the positive charge. Works, it's simple, or you just memorize cation versus anion. All right, so an aluminum sample, how many protons does aluminum have? In order to be neutral, how many electrons does it have? I didn't ask you about neutrons because I would have to provide you with a mass in order to look at that, right? So aluminum 3+, how many protons does it have? How many electrons does it have? Okay, and the same kind of thing for the sulfur. Sulfur, how many protons? How many electrons? Sulfur 2-, how many protons? How many electrons? Right? So what we should recognize is the fact that the 3+ and they're not going to be equal, right? So the protons and the electrons should in fact be the exact same, except when we're looking at a charged particle. So if they have different amounts, we have to recognize that that is in fact a different amount. So let me see, periodic table. So if we take a look at aluminum, aluminum, it has 13 protons and it has 13 electrons in its neutral state. In its +3 state, I have 13 protons and 10 electrons. Notice that I've canceled out all. So if there are 13 positive charges, right, I have countered all but one of those negative charges, or I call it countered all but 3 of those negative charges. Okay. And the best mnemonic I have for this is I'm positive I lost an electron. The simplest way, I mean, again, it's not necessarily super intuitive in terms of saying, it's not really super intuitive because you lose electrons and you actually go in the positive direction, which feels wrong because losing feels like you should go down, but doesn't. You in fact go up in charge or gain a positive charge. So I'm positive I lost an electron is a good way of looking at it. All right, sulfur on the other hand, sulfur has 16 protons, okay, in both cases, 16 protons. And if the neutral one has 16 electrons, and it's going to have 2 additional, the source it got it from, it would have to get it from some other atom in order to become S2-. So it gains 2. Again, if I subtract those 2, I end up with a -2 answer or -2 charge, okay, or 2- as we write. All right, same question. How many electrons are in titanium 2+? How many electrons are in phosphorus 3-? So predicting ionic charges is an important part, and we're going to walk through this in class. We're going to jump ahead and we're going to talk about valence electrons, and we're going to talk about group names, and we're going to talk about all of those things. So I'm going to hold off on kind of predicting these charges. It's pretty straightforward, but it's going to be a really important aspect of doing a lot of this, determining a lot of this calculation. So yeah, so we'll talk about this in class. I can certainly say that anything in group 18 should be 0. In fact, I'll just put these values up. Oh, it's actually right down here, isn't it? Yeah, so we'll talk about the octet rule. We'll talk about this table and we'll fill it in a little bit. And we'll talk about metals versus non-metals and the different names of the different groups, okay, and periods and all that stuff. Polyatomic ions, these are ions that act as if they're active as if they're atoms or ions, okay? So, I can say, oh, chlorine forms a -1 charge. Well, we also have all of these other versions of it. Carbonate forms CO3 2-. So carbonate would be CO3 2-. That's what it looks like. Although it's a group of carbon with a bunch of oxygens, it is always going to remain that. You're not going to break that apart at all. So anytime you see a polyatomic ion, you automatically write it out. You act as if it's like an ion that always exists. Oh, polyatomic ions are molecular because the way they're bound, covalently bound, molecular ions. And then oxyanions are simply nonmetals, typically nonmetals, but not always. So why don't I not say that? I'll say an atom, a central atom with oxygens that are bound. Like all of these are pretty much oxyanions, right? Carbon bound with oxygen, chromium bound with oxygen, phosphorus bound with oxygen, right? Chlorine bound with oxygen. So oxygen does a really good job of creating these oxyanions, which are just polyatomics. Here's a list. This list is also at the end. It's going to be an important thing to memorize some of these. Anything with a star, I've kind of highlighted as something that you should probably know, something you're going to see more often than not, or you should be able to recognize those, especially the nitrates and sulfate. So anything with a star should be known. Okay, good. So we're gonna talk about this in class, but here we have the periodic table with all of the different charges that we might see. And what you're going to notice is the group number generally leads to the ion that you're going to see, at least on the left-hand side. Group 2, you're going to have 2+. Over here on this side, notice that the noble gases don't have anything. All the things in group 17 form the same. In the group 16, these two definitely do, these not so much. And then over here, I don't really trust those. And there's a reason why, and we'll talk about it. What you'll notice here in the middle is iron forms two different oxidation states. Manganese actually forms something like 9 or 10 different oxidation states, both plus and minus. Chromium, two different ones. Copper, two different ones. There's a handful that are very specific, like I can definitely tell you that zinc is always 2+, cadmium is always 2+, silver is always 2+, and aluminum. Those are always going to be what they are, and we'll have that list. But there's what you notice down here is there's variation in oxidation state. Now I say oxidation state, and that is essentially charge, or I should say expected charge. But again, we're going to be covering this in class. You don't really necessarily need that for this next little bit here. So ionic compounds. So it's the transfer of electrons that I mentioned before. Contains metals and nonmetals. We haven't really talked about what metals and nonmetals are. We will, but I can simply tell you that this little ladder right here, anything on this side is going to be a metal. Anything on this side is going to be a nonmetal. And anything that kind of touches this line, there's a handful, but these are going to be called semimetals or metalloids. Okay. Okay, good. All right, so this comes down to ionic compounds. So all compounds are electrically neutral. What is the formula for compound between calcium and bromine? Okay, and so if we look back at our table here, we see that calcium forms a 2+ and bromine forms a 1-. So actually, you know what? We are going to do these in class as well. And then we're going to talk about oxidation states in class. I think that'll be a good exercise to do in class. So yeah, so we're going to do that in class. I will record the next video for 12.7, which is going, or 2.7, which is going to be on nomenclature. So I'll get through the nomenclature stuff, but we're going to talk about the charge, and we're going to talk about oxidation states in class and the periodic table, because I kind of want to lay it out and make sure everyone's on the same page with it. So yeah, that'll work.